we look to the correctness of the vector clock based algorithm. First property we want to prove is the validity, which says that if a correct process causally broadcasts a message M, then the correct process will causally deliver the message M. We assume that the process broadcasts a message M, so it means M is causally broadcast by a correct process with some vector clock VCM. And that vector clock is either equal to the local vector clock of the process at send time, or higher only at the element of that process in the vector clock by the outstanding earlier causally broadcast messages that are not delivered. This mechanism is guaranteed by incrementing the sequence number here, as you can see in the code. So by the reliable broadcast validity, M is eventually reliably delivered at PI, and also all the earlier outstanding causally broadcasts are delivered. So at delivery time, the local vector at that process can only increase. So eventually the vector clock associated with this message will be less or equal the vector clock of the process, and M will be causally delivered. Now let us look to agreement. An agreement says if a correct process causally delivers a message M, then all correct processes will causally deliver the message M. So assume then that M is causally delivered by a correct process PI. That is the first assumption, which if it is causally delivered, it means that PI causally delivered all messages causally before M. And these messages must have arrived there by a reliable broadcast delivery. Therefore, by the agreement property of reliable broadcast, every correct process reliably deliver M and all causally preceding messages. This is agreement of reliable broadcast. And because they deliver all causally preceding message, hence every process also is going to causally deliver M, and that is what we want to prove. Now let us look to the causal order, which says if a process causally delivers a message, then it has causally delivered all preceding messages. So let us see what we can do here. So assume we have a process P, and P reliably delivers M with this vector from a process Q. So we have a message coming from a process Q with that vector timestamp. Now let us look to an arbitrary field in that vector timestamp, and we call it R. So that specific field is a number of messages causally preceding M from R. Now the vector timestamp at P stores the number of messages causally delivered for each process. For example, any arbitrary process R. So for some R, it might be the case that the vector timestamp of the message at that field is greater than the vector timestamp of the process for that specific field R. And that implies that there is at least one message from R that is causally before M, which of course it is not delivered at P. So the algorithm does the following. P will wait to deliver M until the vector timestamp for each field of the message is less than the local vector of the process at each element R. So M will not be delivered until all causally preceding messages are delivered. We are going to see an example of that soon to understand this property. So assume we have three processes, P1 to P3. P is P1 and Q is P3. P1 has associated vector clock, and Q has associated message, which the message include the vector with the values x, y, and z. Now, if y is greater than y0, it means there is a message m prime, say from P2, such that m prime precedes m, and m is not yet delivered by P1. And therefore, P1 will wait until that element, the second element in the vector, is greater than y. And that happens because that element will increase until eventually it becomes y sub I, and y sub I will be greater or equal y. At this point, all messages before that message will be delivered, and then m will be delivered.